Oh, there's something is not quite. Can all of you hear me? So let's activate chat. Would you say something if you can hear me in the chat room? Okay, good. So let's get started. I always find it confusing to use this software. Maybe video is not on. Okay. Okay. So can you also see me in the screen? Would you say yes or no?
Yes.
Okay, good. Thank you. And let me share screen. Okay, so welcome to the second lecture of this Introduction to Logic for Computer Science. And what we're going to cover today is, I mean, for some of you who are already familiar with the logic or maybe mathematics, it's going to be a bit boring. I mean, because we will cover very basics of logic, but I think it's always good to set up, I mean, make sure that everyone are on the same page. So we're going to cover very basic things about the propositional logic, including the syntax, formal syntax, and the semantics. And so if you already know everything, you can relax and maybe, because I can't really see you, and then I don't think anybody can see you, you can just sleep, and that's not a problem at all. Okay, so let's do let me make sure that's, so you can, all of you can see the screen as well, right? The slides. Is it okay? Okay, good, thank you. And just like before, if you see any problems throughout my lecture, you can raise your hand. Also, you can type in some, please raise your hand and then type in something in the chat room. And that will kind of help me notice some problems, I mean, immediately. So what we're going to cover today is the basics of propositional logic, and we'll talk about the syntax and semantics. Likely, we won't have time, but maybe at the beginning of the next lecture, I'm going to explain to you how to encode some interesting problems into propositional logic. And then we can call an existing solver for propositional logic to solve problems like Sudoku or the existence of Hamiltonian path and so on. That's not the focus of this course, but it will show you that what kind of things you can do with propositional logic. So if propositional logic, the name is very fancy, but I think almost all of you already learned about it in high school. And if not, then if you have an experience of any programming languages, you already are exposed to this propositional logic. They are nothing but the Boolean expressions in typical programming languages. And but it's a kind of systematic study about these Boolean expressions. And then there's also one big difference between Boolean expressions in programming languages and what we focus on in study of propositional logic, which is that in the propositional logic, we care a lot about understanding the interaction of so-called logical connectives like and, or, negation, and so on. So in some sense, the study about propositional logic is really a study about how these logical connectives are interacting with each other, what are the computational challenges that they are imposed, what these connectives raise. Okay, so these are the kind of things that we focus on. And then some terminologies perhaps I'm going to use throughout this lecture, maybe throughout this entire course, is that I'm going to call what you will typically call Boolean expressions in programming languages as a sentence or formulas and the propositions when I talk about propositional logic. And if I look back, what I typically do, I use the word formulas a lot, but sometimes I will use the words like sentences and then propositions. But they all mean the same thing. It will mean some expressions in propositional logic. And as I will explain later, propositional logic consists of, is built from very basic ingredients. These ingredients are so-called atomic propositions, and they will be either true or false, so they are constants, and or so-called propositional variables. So one big difference between propositional logic and predicate logic is that in predicate logic, or maybe first order logic that we'll study later, we try to understand how these so-called propositional or Boolean variables are defined. What does it really mean? But when we study about propositional logic, we don't really care. So these Boolean variables, we only care about is they have a value either true or false. But whether it means like Hong-Seok is teaching this course, that kind of things we don't really care about it. We don't care about where these Boolean variables arise. We just say they are given and they have either value true or false. And then we will study the consequences of these propositional variables. And propositional variables having certain values. And then sentences are formed from these atomic propositions by logical connectives. And then the whole purpose of studying propositional logic, as I said, is to study some properties of these logical connectives, and then there's some computational properties about this. Okay, and then while studying about this propositional logic, we will see very important concept called logical consequence, valid, and then also some satisfiable formulas and valid formula and so on. So in some sense, studying about another big objective of studying propositional logic is to expose you to these kind of very basic concepts in logic, which will play a very important role, not just in the propositional logic, but in first order logic later. Okay, just to sum up, propositional logic is nothing but more systematic study of Boolean expressions in programming languages with a big emphasis on logical connectives. And here are just some examples that I want to show you. So let's say in this example, we have a 3 propositional variable, ABC, that can mean anything. But let's say A means Alice is an architect. We use A twice in this sentence because it's related to A. B means Bob is a builder. And C means Charlie is a cook, okay? But ABC can be anything. It doesn't really matter. But associating ABC with these 3 sentences may help you to follow what's really going on. And then we're gonna think about the 3 sentences or 3 Boolean expressions. The first Boolean expression says not C, which in this natural language sentence means Charlie is not a cook. Okay, because the C means Charlie is a cook, its negation means Charlie is not a cook. A or B means Alice is an architect, while Charlie is a builder. And B implies C means that if Bob is a builder, then Charlie is a cook. So these are the 3 compound sentences. So by compound, I mean non-atomic propositions. So these are the 3 compound sentences. So here's just some exercise I want you to solve. Assume that these 3 things are true. Then is there anything that you can say about A? Maybe you can say about A is true. Well, maybe you can say A should be false. Or maybe you can say we can't say anything about A. Okay, so these are the questions that I want you to think about. So, and this Zoom software, I can kind of make a poll. So maybe I will try to run this poll in maybe 30 seconds, so that where you can vote one of the 3 options, either it's true, false, or don't know. Okay. So think about it, and then I will soon start the poll if I manage to run this software well. Okay. Oh. Okay, this. Okay, so yeah. Launch a pool. So yeah, I will give you 30 seconds, please voting. I mean, I can't really see who votes what. So if you want to just, you can just do whatever. That doesn't really matter. Okay, so let's stop the poll, and then I guess maybe you can see the result. So about 22 students said it should be true, and actually the answer is A. The A should be true. So let's see why that is the case. So I mean, the answer is A should be true, and you can think of it like this informally. We said Charlie cannot be a cook, but then the last sentence or last formula said if Bob is a builder, then Charlie should be a cook. Because Charlie is not a cook, the last formula implies that Charlie should not be a builder either. Okay, because if Bob is a builder, Charlie should have been a cook, and that contradicts with the first sentence that we have. So from first and the last sentence, we got the information that Charlie is not a cook and Bob is not a builder. Now, if you look at the second sentence, it say that either, no, not either, Alice is an architect or Bob is a builder, but the second option is gone from the first and the last. So that implies Alice should be an architect. Okay, so this is, I mean, if you are not familiar with, this type of reasoning in the beginning, it may be a bit tough, but this is a kind of reasoning. Once you get used to it, you can do it quite easily. And then if you study the propositional logic, you can do this type of reasoning more systematically. And furthermore, this result, which means this three sentence implies A, or entails A, is independent of the interpretation that we associated with these three propositional variables here. ABC means something completely different, then we get exactly the same consequence. Okay. So, to do so, we need to have a more systematic study about the syntax and semantics of propositional logic. So that's what we're going to do now. And here's the definition or syntax of the propositional logic. And one way to think about propositional logic is like learning a programming language. A bit strange programming language, which is pretty simple and which is very declarative than imperative. Okay, so the syntax of this new programming language called propositional logic consists of like this. It's parameterized by a set of propositional variables. So in this case, it's a set of so the propositional variable x, x1, x2, x3, they correspond to ABC that you see in the previous slide. So that can be either true or false. And then we have countably many propositional variables. And these are the ones that we can use to build more complicated propositional logic formulas. And then formulas in propositional logics are defined inductively. If the base cases are either true or false, and so they are the very basic case, or it can be a propositional variable xi that belong to this capital X that I highlighted in the slide. Or we have two ways of building this formula or propositions from existing one. The first is to put negation. The second is to put two formulas by conjunction and disjunction. I'm sure all of you are already familiar with something like this in your experience with programming languages. But this is a more kind of precise definition of what propositional logic is. And then we will usually propositional variables, which in programming language correspond to Boolean variables. We're going to use the symbols like X, Y, Z, and P. And then all this by nots, and then or are called negation, conjunction, and disjunction, and they are called logical connectives. And we use this Kali graph f of x. So let me highlight this. I mean, this guy to denote the set of all formulas. Okay, so this f kind of represents the word formula, and this inside the parenthesis x means the basic propositional variable that we can use should all belong to this set x. Okay. But then at this point, you might wonder, I mean, when you learn about this propositional logic in perhaps your high school or maybe in your experience in programming, you saw lots of other connectives like implications, and then some other connectives are like, no, not this, yeah, like by implications, sometimes exclusive or, and then maybe sometimes when you use and, it doesn't have to be a binary, it can have a lot of things and so on. And in fact, all of these can be defined in terms of the logical connectives that you saw. So I will give you a few minutes, maybe 2 minutes to fill in the blank in this, or the question mark. And also, I will, I mean, if I, another question is, I want you to think about a single connective that can be used to define everything. The last one is that actually and cannot be that single connectives. So I'm assuming we have a false, true, and then the propositional variables. And by connective, I mean one of these and, or, not, implications, and so on. Okay. So the last question is that single connective that will allow us to express everything cannot be and. So and is not sufficient. So that's the claim, and that's actually true. And if you solve this exercise 1 and 2, I want you to think about why that is the case. So I will give you maybe 3 minutes to think about all of these questions. And if you have any questions while you're solving it, you can ask me using chat. I mean, if you don't want to talk to everybody, you can ask me questions in private chat as well. Okay, try to solve this until 9:21. Yeah, okay. So this is, I mean, I think the answers are pretty easy. So, I mean, if you already done it, and if you haven't done it, and it's again not very difficult, it just takes a bit of time. So the first one, because by implication is implying both sides, that you can just say F by, I mean, if and only if F2 is a just conjunction of F1 implies F2 and F2 implies F1. And then we can rewrite this implication in terms of a not or, as you saw in the first line. Exclusive or means that the values are different, so only one of them is true. So we can directly express it using conjunction, negation, and disjunction. So say F1 or and not F2, or not F1 or and F2. So that means the first case, F1, only F1 is true. The second case, only F2 is true. And indexed conjunction and index disjunction is just, I mean, the multiple applications of this conjunction and then disjunction. By the way, if n is equal to 0 in both cases, so we have an index conjunction over nothing. Also, bottom, that we have an index disjunction over nothing. Then we have to make some decision. We can't really do something like this. So in the case of a conjunction, we take it true because true is in some sense unit or identity for conjunction. If you conjoin anything with the true, it's just the same as what you started with. So true is, in a sense, identity with respect to the conjunction. False is an identity with respect to the disjunction. So the convention that people take is if n is equal to 0, then the index conjunction is equal to true and index disjunction is equal to false. More precise, I mean, the more formally, if later you somehow see the connection between conjunction and disjunction, and lattice theory, this and or are related to, I mean, greatest lower bound and least upper bound, and false and true and false. It's the choice of true and false I mean, they are consistent with that interpretation. Okay, for the second questions, the answer that we can use is implication. So if we use implications, then, I mean, so say if we plug in F instead of F2, if we plug in false, so then that using implications, we can encode the negation. Also, if we have able to encode the negation and implication, we can essentially encode everything, conjunction and disjunction and so on. A bit more challenging part is the last question. The challenge that the last question is we can prove this by using so-called monotonicity. We say, if suppose we have a propositional logic and the only thing we have is a conjunction, and of course we have a true and false and propositional variable, but the only logical connective that we have is a conjunction, then this logic or restricted segment of propositional logic will have satisfy so-called monotonicity property, which means if we have a formula or if we have a sentence in this case, I mean, in this restricted fragment, and if we replace the truth value of one variable there from false to true, then the truth value of the entire formula will go up. If it's already true, then it will remain true. It will be a false, then it may remain false or maybe become true, but it will never the case that original formula was true, and then the new formula that you obtained by changing the truth value of one propositional variable will become false. So we'll never make formula from true to false, okay? Changing value of a propositional variable from false to true only will increase the truthfulness or trueness of the formula that we have. So that's a properties of this restricted fragment, but the entire the propositional logic doesn't have that property. For instance, if you have not x, okay? So then if x is, so maybe just write it here. So if I have a not, thick. If I have a not x, if x is false, so then the entire formula is true. But if x is true, then the entire formula becomes false. So it doesn't satisfy the monotonicity property. So by thinking about this generic property of the entire language, restricted language, we can show that the end is not enough to encode all the connectives in propositional logic. Okay. No, erase. Okay, so let's move on. So then we have take some conventions, which are essentially saying, if you formally, we have to put lots of brackets, but we're gonna omit essentially almost all of them, and then rely on the convention. And the convention is that the negations is the tightest bind the tightest. So here the negation bind the tightest, but then after the negations, conjunction binds next bind the tighter than the implication. So what the formula that you see here, it's a bit strange. Okay. So the formula that you see in the fourth line of this slide means, what's written there. Okay. So throughout the lecture, I will adopt this convention. And then last year, when I teach this course, some students were struggling to put the parentheses in the right way. So if you get confused, always raise your hand and then just ask questions in the chat box. So then I will write down put the parentheses. It's quite easy in this interactive online environment. So just ask a question, whenever you get confused. It's very likely that if you got confused, some other students are confused as well. Right. So that's a definition. We just defined the syntax of propositional logic. And then I explained some of the conventions we adopt. Some good way to understand the propositional logic is in terms of the syntax trees. You can think of this syntax tree as a parse tree of the propositional logic formula. Okay? And we can represent every formula as a syntax tree. So here's an example of the syntax tree that you will see. So the formula not blah, blah, blah. So so now this guy can be represented as the tree that you see. Now is the operator that applied at the topmost that sits at the top of the tree. And then the end is the next. So that's why we have the edge from the negation to the end. You see here. And so on. So this is a kind of representations of this formula. Okay. And then we record sub-formula of formula F as all the subtrees. So essentially, yeah, so the word sub-formula have intuitive meanings. And then more formally, it corresponds to the subtrees of this syntax tree. And the one good kind of, if, say, later you implement, some kind of tools for propositional logic formula, then your program is likely to work on this syntax tree representation of propositional logic formulas. And once you view this formula as a syntax tree, then there is a very natural way of defining some concepts or reasoning about these formulas in propositional logic, which is using inductions. Just imagine that we want your data structure that you employed to implement the formulas in propositional logic is a syntax tree. So you will literally implement it in your computer, the propositional logic in terms of the syntax tree that you see here. So then now suppose I want to write some functions that take propositional logic formula and return some value. Then maybe the easiest way to do it is to using recursions. Well, maybe in this context, it's an induction. So and that's correspond to this so-called structural inductions that I'm gonna explain now. The structural induction means we're gonna want to define some concepts for some mappings from the propositional logic formula to something. And the inductions say we can do it by doing these two things. One is we define what should happen for the base case. And then we define what should happen for this logical compound case, like a logical connective case. But in the second case, we can use inductions. So here are the examples of doing this. So suppose we want to define a function that take logical formulas and then return the number of symbols appearing in the formula. And then we can use this structural induction definitions to define this function size. More programming terms, we are really defining the recursive functions that take logical formulas and return some number. So this definition said size of true, the base case, true, false, and propositional variables. In that case, the value is equal to 1. And then we also have to define the inductive case. But when we define the inductive case, we can use induction hypothesis, essentially. Or in terms of programming language terms, we can make a recursive call. So we say the size of f is just, we make a recursive call, and then we just add 1 because of the extra symbol called negation here. And then for conjunction and negation, we can do essentially the same thing. Make a recursive call twice for f and g, and add number 1 there. So I think the best way to understand this is to actually try something. So, I mean, just try to solve both of these exercises, and especially the main exercise is exercise 2. Try to define functions that take a formula and return a set consisting of all the sub-formulas of the formula that you are given. Okay, try to define this, solve this exercise 2. I'll give you maybe 2 minutes to do so. Because screen is shared, I think this private chat maybe can be seen by everybody. So some students ask me about why we need countably many variables here. And likely it's not, that assumption is not absolutely needed, but I don't quite remember. So if at some point we talk about some algorithmic aspect, that countability might matter. But for instance, but some other result maybe become independent. Especially we will talk about compactness theorem. Our proof might rely on the countable case, but the general theorem itself is, I think, is true for arbitrary case. Okay, so let me just solve the second question. And let's see. So here you will see my bad handwriting. Okay, so we have to define this function sub for sub of the base case, like a true. In this case, is just it returns true as a formula. And then the false and propositional variable case, they are all the same. So again, false, propositional variable x, it's a singleton set x. Then for negation case, we make a recursive call that will return all the sub-formula, including f. And then we have to add one more thing, which is the formula itself. So that's what we're gonna do. And then the sub-formula for f and g, that's same as we make a recursive call to get sub-formula of f and sub-formula for g. And then we just add one more formula, which is f and g. And the treatment of OR is exactly the same. Okay? And some students who took my course on programming languages, there is more formal or maybe more esoteric or more abstract way to understand what's really happening in terms of initial algebra and so on. But I mean, at this point, all you need to do is these formulas can be represented as a trees, and then we can essentially use induction over the trees. Okay, so now we define the syntax as for the propositional logic, and we define 1, 2 to do something with the syntax, which is inductive definitions. Now we're going to use this inductive definition to define semantics. And syntax is it's a kind of specification about what we can write, but semantics really means it's a specification of what we wrote actually means. So since I'm sure that some of you studied about like automata theory, context-free grammar, and so on. They're all related to syntax, and semantics is a bit different, and it's a it's something maybe you will study, you already studied in more like in semantics course in the or programming language courses. And semantics, its purpose is to map this syntactic element to the mathematical model. And in the propositional logic case, it's really, really simple. I mean, although all the things written there looks very fancy, really what we're gonna do is we'll map its propositional formulas into into 0 and 1 essentially, or into precisely into a mapping of from the truth assignment to propositional variables to 0 and 1. So let me explain this more precisely here. So the semantics is defined, it's defined in terms of the inductive definitions that I explained before. But it has some ingredients, okay? So it's what you can say it's parameterized by what I call assignment. So to give us semantics, because our propositional logic formula contains propositional variables, we have to provide a meaning to these propositional variables. So what's called assignment here is a parameter of the semantics, and that parameter give a meaning to all those propositional variables. So it's a mapping to set up all the propositional variable to 0 and 1. So it will tell us whether propositional variable A is true or B is false and so on. And then this semantics say, once we are given this assignment for propositional variables, here's the systematic way to lift it to all the formulas over these propositional variables. That's in this slide written as A hat. So A is given things, A hat is something that we are defining using this given A. Okay? And its interpretation, it's called assignment, or sometimes it's called semantics, or sometimes it's called interpretation. And that definition is what you exactly, this corresponds to your intuitive understanding. So A hat of false should be 0, and A hat of true should be equal to 1. And then for all the propositional variable, we have to follow what's given. And for other cases, negation and conjunction and disjunction, it has the usual interpretation. So negation means not. So if it's, the original formula is equal to 0, meaning false, then the not F should mean true, and otherwise it should mean the false. And then conjunction means conjunction, and disjunction means essentially disjunction. Okay. But the point of showing this is, here's a formal way to capture your intuitive understanding of propositional logic. And later, when we try to prove something about the propositional logic, this formal definition is the things that we're gonna use. Yeah, so here's some simple exercise. I'm sure it's quite easy, but I'll give you maybe 1 minute so that you can do some calculation for, compute the semantics of this A hats of the first guy, and then also A hat of the other one. Okay. So I'll give you 2 minutes to finish this exercise. Yeah. Okay. So let me just show you the solution for the first one. Let me, okay. So the if we do the calculations, oh no. So we can say in the A heads, we know the A head of, first compute A head of X and negation of Y. And to compute this, we need to figure out the A head of X, which is same as A of X. And that is, in this case, is equal to 1. And we also need to compute A head of negation of Y. But we know the value of the Y on the assignment A is 0. So if this negation has to value 1. So then this one, for each conjunct of this conjunction, we have the value 1. So the value is equal to 1. And then that means A head of X and negation of Y or Z. It should have a value 1 because the semantics say, for semantics of disjunction, so if one of the disjunct has the value 1, the entire thing has the value 1. So you can do calculation like this. It's not a big, not difficult, and you can actually write program that computes this, do this evaluation. Okay. See. Okay, so let's move on to next. And from now on, I'm not going to use this. When I write A hat, I'm gonna omit this hat from the symbols, and then I will just use A for both given assignment for the propositional variable, as well as the semantics or assignment for the propositional logic formulas. So don't get confused. Again, throughout this course, I will adopt conventions like this in many places. So if you have any problems or get confused, you can raise your hand and then ask me questions. And then I think when you learn about propositional logics in high school, at least this is what happened to me when I learned about this maybe more than 30 years ago. And I learned in terms of a truth table. So the truth table said, oh, conjunctions, if the value of two argument is something, it has the value 1. Disjunction has a value, some other cases, and so on. So these are the kind of truth table we learn. And then the purpose of showing this slide to you is that, I'm sure you also learned about this when you learned about logic before, but this interpretation or the semantics of, especially disjunction and implication in logic is not quite semantics of disjunction and implication in the natural language. If you say or in the natural language, we usually mean exclusive or. So we say, oh, I either go to home, or I go to home, or I stay. I go to home or I go to office. So then we say only one of the option is possible. But in the case of disjunctions, if both of them are true, still that the entire disjunctions is going to be true. And another things that people get confused quite a bit is about implications. So in the case of implication, so here are two cases that I highlighted. It's not get highlighted as I wanted, but if the assumptions is false, then whatever happens in the conclusion side is always true. Okay, so this is a kind of particular interpretation of implication that we're gonna use, and that corresponds to so-called classical logic. So this is some side remark. Some logicians are very unhappy with this interpretation of the implication. So they use some different notion of implications, especially something we are not going to cover this, but there are some variants of the kind of logic that we are learned, which are called intuitionistic logic, or sometimes called relevant logic. There they use a different understanding or different semantics of this implication. So for instance, in that kind of logic, assumption being false doesn't necessarily mean the entire implication is true. And then funny fact is that this type of logic, initially it's kind of invented purely based on philosophical reasons, but they found applications in computer science. Intuitionistic logic has a huge impact in the design of type system. Relevant logic has been used for automatic program verifications. Anyhow, okay, so here are some exercise I want you to do. So then this exercise has a lot of words. I think the typical exercise in logic, especially at this stage, is, I mean, just understanding the problem takes a lot of time. So this is that kind of problems. So here are just some phenomena in the natural language. We describe in the natural language. And I want you to formalize what's going on here in terms of logical formula in propositional logic, and do some reasoning about this. Okay. So in particular, here are the question that I want you to solve, and maybe I will make a poll. So the question is it possible that all those four statements can be true at the same time? And so that the answer is either yes or no, and we make a poll about this. And of course, if you want to cheat, you can always go to the next slide and get an answer. Okay. So I will give you maybe, I think I'll give you maybe 5 minutes to read these descriptions and then understand what happened. I mean, the descriptions say I have a device which has a 3-part. Thermostat means 온도계, pump means pump in Korean, warning light means, yeah, there's some 불 in this device, and then the descriptions about some relationship between these devices, some components in this device, and from this descriptions we want to do some reasoning. Okay. I'll give you, yeah, as I said, 5 minutes. Start the poll. Sorry. Yeah, sorry, I think I can't start another poll here. So I'll just give you an answer after 2 more minutes. Yeah, okay. So the answer here is yes. So these four statements can be true at the same time. And I mean, you can just do some reasoning based on all, just by putting all these sentences in your mind, or you can form, I mean, we kind of translate all these formulas into propositional logic formula, and then check whether that formula can be satisfiable or not. So this T means the thermostat is broken. So this T represents thermostat is broken. And then this P means pump is broken, okay? So the first sentence means the thermostat or pump is broken. And the second sentence say if thermostat is broken, its pump is broken. So that's what this implication captures. The third means the pump is broken, the light is on. So W means the light is on. Then the thermostat should not be broken, and so on. So this, what you see at the bottom is the representations of these four sentences. And then we can try to find some truth assignments for these T, P, W, so that the formula F or sentence F, it becomes true, okay? And then that's possible under the following assignment. If T is equal to 0, so thermostat is not broken, but then pump is broken, the light is on, and that will make this whole thing satisfiable. And in fact, what really happens if you draw the truth table, I think this is how you perhaps learn about the logic long time ago. So we just draw all the possible truth assignment for propositional variable in each line. So this is the assignment of the truth variables. And then we say what's going to be the truth value of the entire formula. That's what's written on the other side. So then because there are 3 variables, there are 8 possibilities. And then if you just enumerate or get some meaning for this formula F in all those possibilities, there is only one case. And actually, so that case is what I just described you to before. So these are the kind of things that you can do. But I think the more important reason is if you once you have this formal understanding, formal description about what this formula or sentence means, then that opens the door for more systematic studies for these type of logical formulas in propositional logic. That will include more mathematical study as well as computational study. And here are some very important concepts of the propositional logic formula in the semantics that we will use quite a lot. So we say, if we have a formula F, so here, and then we have an assignment for propositional variables, A, then we said this, we use this symbol A, some symbols and F. In Korea, it's ya. So this one, it means that the A satisfies F. So that's how I usually understand this. It describes satisfaction relationship, but you can also read it by saying F is true under A, or A is a model of F. But all of the cases really say under the situation of A, formula F becomes true. So that's what this one is describing. And if a formula F has a one model, so if formula F is true under certain A, then we said formula F is satisfiable. So the for example that we saw before, actually there's a one truth assignment that will make the formula F true. So there's a formula F that you saw in the previous slide is a satisfiable formula. But not all formula is satisfiable, and those kind of formula is called unsatisfiable. So satisfiability means there exists a single, or at least one A that make F true. Unsatisfiability means that formula F is gonna be false under any assignment. If formula is true for all the assignments, then we say the formula F is valid. So the satisfiability and validity is different. Satisfiability is about one existence of at least one good assignment. Validity means the formula is always good. So its formula is true under all the assignments. Okay. So these are the basic concepts: satisfaction relationship, satisfiability, and the validity. These are the very basic concepts in the logic. And I think okay. And then Boolean satisfiability problem. This is more like a computational problem. And then the problem is the following. It said that it asks us to design an algorithm that takes a formula, propositional logic formula F, and then check whether given formula F is satisfiable or not. So, and in fact, there are many programs, what's so-called set solver, that solves these type of problems. And then I think actually one of the exercise or programming project you have to do is to implement this type of satisfiability solver based on the algorithm that we learned in the class. So now here's just some exercise I wanted to think about. Suppose we have a program that solves this satisfiability problem, okay? Can you somehow change the program a little bit? So in some sense, you have a subroutines that solve this satisfiability problem. Now the question is, can you somehow change it so that it can also check for validity? You can come up with some checker for validity very easily by using this existing program. So I will give you maybe 1 minute to think about this problem and solve this. Okay, so here's a way to solve this. And maybe new page. Okay, so here's just a way to design an algorithm. So we want to design the validity checker. And they will take propositional logic formula F. Okay, so that's our program. The first step this program does is, roughly what we're gonna do is we will use this satisfiability solver to check whether this given formula has a counterexample or not. Okay, validity means this formula F is true all the time, and then that means the formula F is valid if you can't find the counterexample. So what we're gonna do is we record set solver over the negation of F. Okay, that we are asking set solver to come up with a counterexample. So then we assign the result to B. And if B is true, so that means our set solver was able to find a counterexample. So F is not valid, so we return false. And yeah, we return false. Otherwise, that means our satisfiability solver failed to solve find the counterexample, so we return true. So that's how you can use the set solver to do the validity check. The idea is the set solver is designed to find a assignment for a formula, but that set solver can be extremely powerful because we can use it to solve all sorts of counterexample we want to check. Okay, so that's how this. So just to sum up, we define semantics, and then here important concept are satisfactions and satisfiability and the validity and subproblem. And then there are many valid formulas that you learn in the lectures. Maybe in high schools. And one of the formula that you learn about is, I think, the De Morgan's law, which means if you move So De Morgan's law is given here. So if you move negation from the outside of the formula to the inside, just this and becomes or becomes and so on. And then also, you may or may not have heard about this distributive law, which means that if you have a disjunction outside and a conjunction inside, then we can change this and we can move this outside disjunction inside the conjunction. And then that also can be done for the conjunction and disjunction case as well. So I ask, there's an exercise which say prove these two using the semantics, the first and last two. So I'm encouraging you to solve this exercise. It's not a difficult thing at all, but if you haven't played with the semantics, this will help you to get familiarized. Help you get used to the semantics of this propositional logic. And then there's also notion of logical entailments. That is perhaps something that you encounter a lot often in practice, but in real life. And in real life, we say, oh yeah, blah, 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 follows because it's a logical consequence of some assumptions you make. And these are the kind of arguments that you hear often in practice in real life. And this entailment captures or formalizes that notions. So we say that a formula F, so we say formula F is a consequence of a set of formula S. So G is a consequence of a set of formula S. Okay, so G follows from S. So this curly S is not a single formula. It's a kind of multiple formula, and we are thinking about conjunction of all those formulas. So assuming everything in S is true, we are interested in whether G is also true or not. Okay, so and then this entailment expresses exactly what we care about in this such a scenario. We said formula G is a consequence of a set of formula S if every assignment to the propositional variable that make everything in S true, that all should also make G true. Okay, so whenever S is true, and every formula in S is true, G is true. So that if that is the case, then we say that G is a consequence of a set of formula S. This is exactly correspond to your intuition of the logical consequence. And we also say two formulas are logically equivalent if for any assignments that these two formula have exactly the same truth values. Okay, so maybe if F and G doesn't have to be true all the time, but when it's true exactly the same, whenever F is true, G is true, and vice versa. So they have exactly the same cases when they are going to be true. Okay, and then we use these notations to say this F and G are logically equivalent. So we use notation on the top to say G is a consequence of a set of formula S, and then in the bottom case, we use this triple equal sign to say F and G are logically equivalent. Here's another exercise I want you to think about. Suppose, just like before, we have a subsolver. So, and then now this time the question is converted to a checkers for entailment and then equivalence. Okay. So assume that this S is a single formula in this question, and then solve this question. So I will give you again 2 minutes to solve the problem. Yeah, okay. So let me show you the answer. So this case, maybe erasures. So for this problem is also that we can use essentially the same principle. So we want to say entailment checker. So this whether we want to check whether something entails or not. So we are given two formula F and G. And what we want to check is we want to check F entails G. Okay. G is a consequence of the formula F. So here we are thinking about a situation where curly S that you see in the slide is a singleton set. And then what we do is that we are asking set solver to find a counterexample of this. The counterexample in this case is a assignment to the propositional variable that make F true, so assumption true, but conclusion false. Okay, so what we have to do is we just call set solver, but this time we said we are asking for the counterexample for this entailment, and then for the counterexample has to be satisfy the assumptions, but it shouldn't satisfy its conclusion. And then we said if B is true, then the entailment is false. Return. Okay. Will return false. Otherwise, return true. So the kind of high-level idea is pretty the same. We use a set solver to find a counterexample, and then absence of counterexample means something, some property we care about is true. And then equivalence check is, I mean, we can directly encode this equivalence check using set solver as well, or we can just invoke this entailment checker twice. So we said return entail, I mean F and G, and we also call entail G and F. So if both entailment is true, that means these two formulas has to be equivalent. So you can write a solution this way. Okay, so now let's see the final case. So because we have about 5 minutes, what I'm gonna do is I will give you some introduction to the final case, maybe just give you some taste of what it is. And then we will talk about this more seriously next lecture. So I will give you about, say a few words in maybe 2 minutes and have a quick Q&A sessions about 3 or 4 minutes. And then we'll continue this lecture in the next Monday. So here's a problem that we want to encode using the propositional logic formula. So this is a Sudoku problem. I'm sure most of you know about Sudoku. There are a bunch of, 9 by 9 squares. And then we want to put numbers between 1 and 9, such a way that every row contains all the 9 numbers. So every row like this should contain, strange, or 9 numbers. Also, every column should contain 9 numbers. And all the subsquare, maybe this is better. So some subsquare like this should contain 9 numbers and so on. So the question is, we want to encode this problem into propositional logic. That's because if you do so, we can actually use this set solver that we discussed before to solve this type of Sudoku problem. And actually, set solver is pretty good at it. And so let's remove this. So then for this type of a question where we want to do encoding, let me just erase here. So for this type of question, when you do encoding, the most important step is to find a way to represent our problem into Boolean variables. So here is the key step of this encoding. The key step is essentially the line that you see on the slide. It says that we're gonna introduce 9 by 9 times 9 times 9 variables. So for every box in the Sudoku problem, we will introduce 9 Boolean variables. So we have a Boolean variable like this. And then, so that's a 9 times 9 times 9, which is about like 700 Boolean variables. And what this Boolean variable has a meaning. So if this Boolean variable is true, if grid position INJ contains number K, okay? So, I mean, if some of you maybe play with the so-called machine learning, but then there you may see quite a bit of examples of so-called one-hot encoding. So this corresponds to so-called one-hot encoding of these numbers 1 to 9. So we have for ij, 9 Boolean variables. We usually expect only one of them is true. So then the way we encode our Sudoku problem is once we set up, I mean, decide how to use this Boolean variable, then we can use this Boolean variable to encode our problem. So here are the 3 properties we have to write. And then the first property is we have to, in a sense, write a propositional logic formula that said each row and each column contains numbers from 1 to 9, all of them. So that's what we have to say. And then the second line is for each of the 3 by square, the block in this 9 by 9 square matrix, they also contains all the numbers from 1 to 9. The last bit is no single square in this 9 by 9 matrix contains 2 numbers. So if we express these 3 things using the Boolean variable xijk, then essentially we can encode this Sudoku problem and ask the set solver to solve this for us. So we're gonna do it next time. So meanwhile, if you are interested in, you can just try to fill in this gap in here. Okay, so that's it for today, and I will maybe stay in about 3 to until maybe 10, 20, and then if you have any questions, you can ask me. Okay, so thank you very much, and let's see you next week. This is not what I wanted.